All right, last time we talked about the theories for rate constants, and a lot of the discussion, a lot of the most important ideas center around what are called reaction energy diagrams, like this one, where you have an energy versus a reaction coordinate. And we'll talk a little bit more about what those things are, well, what the reaction coordinate is, especially later in this lecture. But I skipped over a topic last time, and before we go any further, I want to fill that in because it's a relatively important thing. So I said last time that in this reaction energy diagram, there is reactants, there's products over here, and by following this reaction coordinate, you move from reactants to products, and as that happens, you get up and over the hill. But I always talked about it as if we were going this way in the forward direction. But of course, it's clear that if you started over here, which you perfectly well can, right, just start with a bunch of products instead of the reactants, then you can also go backwards. So this diagram doesn't just deal with forward reactions, it deals with both reactions at once. This is the diagram for an elementary reaction in one direction and its reverse reaction in the other direction. And remember what we talked about before from the principle of microscopic reversibility, that every reaction has a reverse reaction. And now you can kind of see why. If this is the reverse reaction, and if the delta H is negative like this, so that the products are at lower energy, or at least lower enthalpy than the reactants were, then the energy hill is higher going backwards than it is going forwards, but it isn't infinitely high. And so there always will be the possibility, it may be that the reaction's much slower going backwards, but there's always the possibility of getting enough energy to get up to the top of the energy hill, even starting from a low point on the product side like this. There's a lot of implications that follow from this. So for example, as I sort of alluded to here a moment ago, there's an energy of activation on this side, and I've decided or said earlier that energy of activation is basically the same. It isn't quite. I mean, I want to repeat and reiterate that these two aren't really the same thing. There is a difference between the two, but in this class we'll treat them as the same because that's the simple and useful thing to do. So we're going to treat these guys as equal, the energy of activation and the enthalpy of activation, or the enthalpy to the transition state. That's the enthalpy change as the reactants go up to the top, to the transition state here. So this is where the double dagger always refers to. There's an energy on this side, but there's also one on the other side, and you can see just by looking at the diagram that the difference between this guy and this guy must be the delta H for the reaction. And so we have that the energy of activation for the forward direction minus the energy of activation for the reverse reaction is equal to the delta H of the reaction itself, the standard state delta H for the reaction itself. And of course, since the energy of activation and this delta H of activation are the same thing, or we're treating them as the same thing, then that's also true for those two. And then there's a whole bunch of other quantities, right? There's a delta G, a free energy change for going from reactants to products from either direction, and the difference between those two is the delta G overall for the reaction. And there's an entropy change also. And so the difference going forward, the entropy change going forward minus the entropy change going reverse, is the entropy change overall for reaction. And another version of this same sort of relationship is the one we've already talked about, which says that the equilibrium constant, these are all the thermodynamic quantities, right? These guys all over here. And these are all kinetic quantities over on this side. And I pointed out earlier that this is the thermodynamic relationship over here, and these are kinetic properties over here. So this is also a similar type of relationship. The equilibrium constant is equal to the ratio of the forward rate constant to the reverse rate constant. Let's see, I think there was something I skipped up here. I've drawn all the diagrams so far also as if the products have lower energy or lower enthalpy than the reactants do. And for a lot of spontaneous forward reactions, that's true, but it doesn't have to be true. Reaction can be spontaneous forward, doesn't have to be spontaneous forward at all, or product favored at all. And so there's lots of reactions where the products are actually at higher energy or enthalpy than the reactants are. And so I just want to write this diagram down just so people aren't under the impression that this is the only kind of diagram. You can perfectly well have one over here. People oftentimes even write reaction energy diagrams like this with more than one hill, and then they're really talking about two different elementary reactions, right? This would be one elementary reaction, and this would be another one that would come after. So this would be something like A goes to B goes to C, right, where each of these is elementary. This would be B here, this would be A, and this would be C. So you can, there's a fair variety in these reaction energy diagrams, and I haven't written out all the possibilities, but certainly one very obvious and clear possibility is just that the other side has higher energy than the lower side. All right, then there's all these relationships between the forward and reverse quantities, energy of activation, enthalpy of activation, delta G of activation, transition state delta S, equilibrium constant, and so on. Let's do an example. So we have some generic reaction here, A plus B plus C. A lot of these examples, it doesn't really matter what the reaction is. All that really matters are these numbers over here. So for this reaction, we know we're given all these quantities, but for the forward direction. Notice the little f here, forward. And we're also given some thermodynamic quantities, delta H, delta S, and the equilibrium constant, right? The equilibrium constant stands in for delta G here, right? Because equilibrium constant is e to the minus delta G over RT. So that delta G is contained inside this equilibrium constant, at least for a given temperature. And so I say, yes, this is the equilibrium constant, not in general, but at 300 K specifically. Then it wants to know what are the values for the reverse reaction, and we're just using this whole set of relationships up here, pretty straightforward. EAF minus EAR is equal to the delta H of reaction, and therefore the reverse energy of activation is equal to the forward one minus the delta H of reaction. And in this case, I say 50 kilojoules per mole for the forward, 40 kilojoules per mole for the delta H, and so 10 kilojoules per mole for the reverse reaction, for the energy of activation, the reverse energy of activation. Then I want to get this Arrhenius A factor, pre-exponential factor, for the reverse direction, right? And I want to get the reverse rate constant as well. I'm given the equilibrium constant, so I can get the reverse rate constant right away. It's going to be, well, K forward here is 19.6. And the reverse rate, the equilibrium constant is 1.8 times 10 to the minus 2. So that gives about almost 1100 as the value for the reverse rate constant. One tricky thing, or slightly tricky thing, is notice that the forward, given this reaction here, the forward, given that it's elementary, the forward reaction must be second order. The reverse reaction must be first order, so the rate constants are going to have different units. Molar to the minus 1, seconds to the minus 1 on top here, and unitless on the bottom, which means that this guy has units, has units of seconds to the minus 1. And so beware of that, or be aware as you're doing this. All right, now that I have the reverse rate constant, I can use the Arrhenius relationship to get the reverse pre-exponential factor. I just need to divide by e to the minus EA over R, which we got up above, right? That's the 10 kilojoules per mole. And that gives a reverse pre-exponential factor of 6.0 times 10 to the fourth. Once you've got all those numbers, you can construct this whole reaction energy diagram. And people do this routinely, even at the highest levels of research in the current day, oftentimes using not experimental data, but simulated data, for example. You'll see reaction energy diagrams of a sort like this. Sometimes they're kind of modified in the literature, so you don't recognize them. They aren't quite drawn to look exactly like this, but something equivalent to a reaction energy diagram are common in many papers in the literature these days, especially among simulators. And so you can draw this thing pretty much. You know that on this side, the energy of activation is 50 kilojoules per mole. On this side, it's much smaller, 10 kilojoules per mole. And that the delta H of reaction, notice a positive delta H because I gave it that way, of 40 kilojoules per mole. So you can get an overall idea from these relationships and a relatively small number of experimental data or given data about the whole reaction energy diagram. Yes, and then just to sort of complete things, we also have the enthalpies of activation, because we're assuming for present purposes that they're the same thing as the energies of activation. All right, that is all I wanted to say. That was sort of the topic we skipped last time. Now I want to come to sort of the closing topic for this set of notes, which is to talk a little bit more about I-ring theory and what I-ring theory does for us. What's the advantage? I've mostly, almost entirely used Arrhenius theory so far, and that's because it's simpler, and most of the time it gives us results that are mostly what we want. So why use the somewhat more complicated I-ring theory? But one thing I-ring theory does that Arrhenius doesn't do at all is give us an idea for what those values are, what those energies of activation are, what that pre-exponential factor is, and so on. And so I wanted to talk about that a little bit. And to do that, the thing that I-ring theory does is tell us a lot about what this transition state is, this mysterious point at the top of the barrier in the reaction energy diagram. And so let's talk about that for a while. Here's the reaction energy diagram again, and always in all these diagrams, I've had this thing down at the bottom called the reaction coordinate, and I just tell you that as the reaction coordinate increases, then you're going from reactants to products. All that's true, but it doesn't give you any idea what that reaction coordinate might be. I think in a lot of cases people believe, even instructors at the university believe sometimes, it isn't anything real. It's just sort of a heuristic, and it's used that way a lot of times, but it is real, or it can be real anyway. What is a reaction coordinate then? Here's what it really is. It's a collective motion, which means all the atoms are moving at once. You're not just moving one atom or two atoms, you're moving all the atoms at once in a way that when you move along it, you're moving from reactants to products. That's what I've said before. And you're moving along a minimum energy path. What does that mean? Well, let's take a look at some examples and then we'll get a feeling for that. So here's an example. I'm considering this elementary reaction, first order in both directions. It's just a change of conformation from the cis arrangement to the trans arrangement for this double bonded molecule. So I start out with the cis arrangement of the double bonded molecule. If we were in freshman chemistry, we'd draw a diagram like this, right? A valence bond diagram. Basically, you've got some hybrid orbitals here on the carbons. You've got a single sigma bond in the middle that results from the overlap of two parts of the hybrid orbitals, sp2 hybrid orbitals. And then there's a leftover p orbital that's sticking up out of the plane, and that's forming the second bond, right? This is one bond down here, this is the second bond down here. And as long as everything's in the plane, so all these atoms are in the plane, then both of those bonds are full and complete. But we need to go to this molecule over here, which means we're going to have to twist one end of the molecule relative to the other. So let's start doing that. What happens then Well, right away, I mean, the sigma bond isn't affected at all. The rotation around the sigma bond doesn't do anything, so that's always going to stay the same. But the pi bond with the p orbitals starts getting twisted. The p orbitals no longer line up with each other anymore, and now they can't conjugate with each other as strongly as they once did. So the second bond, the pi bond, is now weaker than it was. Keep going, eventually you get the and let me say that when this is happening, the main motion is the rotation of this end relative to the other end, but that's not the only thing that's going on. I say here that bond lengthening is going on, right? Because you're weakening the bond. This was a double bond, now it's not a fully double bond. That means this bond length is getting longer. Also, the bond angles here and here are going to change too, because you're changing the whole electronic structure of the molecule as you're doing this, and that's going to make at least small changes amongst all the atoms in the whole molecule. That's what I mean by collective motion, following some program sort of that moves all the atoms at once in a concerted and collective way. So you reach 90 degrees, now the pi bond has been completely broken. There's, actually I wanted that, yeah. There's now no second bond at all, because these two pi orbitals that are responsible for the bond are completely orthogonal to each other. They don't overlap at all. Rotate still further, and you start to get a little bit more overlap now. I didn't put the bond in there. I guess I probably should. But there is now beginning to be a bond again until you've rotated all the way around 180 degrees. And now there's a new bond again, and because the p orbital is the same when you rotate it by 180 degrees, the new bond is just the same as the old one. So this is all a full double bond again. So that's an idea, or that's an example of a reaction coordinate. It's a rotation around the C-C bond in this case, the C double bond, C bond. Bond length changes and bond angle changes occurring at the same time, a collective motion, yeah. All right, so that's one example, probably among the simplest of all possible examples. And notice, even to sort of talk about it, I had to use sort of some quantum bonding pictures here, which tells you that it's very elementary, right? Anytime you're talking about the quantum mechanics itself, then it's really an elementary step. Let's talk about another type of reaction coordinate. In this case, we're considering a very unusual reaction, and the reason for choosing this unusual reaction is that it only involves three atoms. There's an I2 molecule or molecule over here, and a single chlorine atom over here. This chlorine atom is going to collide with the I2, and it's basically going to steal an I atom from the I2 and form an ICl molecule. So this is what's going on sort of physically or pictorially. I here, chlorine here. Initially they're far apart. At the end, there's a loose I atom, and an ICl molecule has formed. Going down the process in smaller steps, you can get some idea of what the transition state should look like. I guess I didn't say that up here. This is the transition state, right? I should have pointed that out above. It's the point sort of halfway between the two ends, right? From this point on, you're going down. You're at the top of the energy hill, right? You've broken the bond completely. That's what tells you that you're at the transition state. You go this way, and you're going down in energy because you're starting to form this bond again. You go this way, you're going down in energy because, again, you're reforming the second bond again. And as long as you keep going this way, you're just getting to higher and higher energy. So that tells you that this is the transition state. And yeah, all right. And now, what's the transition state in this case? Well, let's look at what's happening. Let's confine all the atoms to a single line for now. In reality, of course, the second atom can come in from any direction at all and collide. But it's simpler if we just consider this chlorine atom coming in from the right-hand side here, moving towards the left, along a line that's lined up with the ICl. As it moves closer, it's starting to form an attractive or favorable interaction with this lead iodine atom, and that's going to inevitably steal electrons, shared electrons, right, from the iodine-iodine bond. And so this bond is also getting longer. I didn't really draw it very well here, but this distance is getting shorter, this distance is getting longer. And as long as everything's lined up like that, we can understand that motion by talking about the values or the lengths of the II bond and of the ICL bond. And we can plot all the possibilities versus on a two-dimensional diagram where R1, this length, is along one axis, and R2, this length, is along the other axis. And then these curves that I've drawn on here, these are contours meant to show the energy. So that means this is high energy up here, high energy up here, and then this valley that's going through the middle here, that's the lowest energy part of the diagram. And this dotted red line shows the lowest energy path, right? You're following the valley bottom as you move along here. As you move along the valley bottom, though, you're going to reach a region where, in order to go further, you've got to go uphill in energy, and eventually you're going to reach a maximum, and then it's going to go back down in energy, and that's the transition state on this two-energy diagram. Looking over here at the sort of more physical picture of what's going on, that's the point where this II bond has gotten very weak, but before the ICL bond has fully formed. And so you don't really have either bond for a moment there, and that's why this energy is higher than anywhere else. This is the point that you have to go through, in order to break this bond and also reform that bond. And you keep going, and now the II bond is lengthening, the ICL bond is shortening. That corresponds to going downhill again. And eventually you reach the products, ICL over here and I over here. And so, if I were to plot the energy of this system following this red curve, I would get something like this, right? It would start out flat here, it would rise, it would go down again and be flat on the other side. This corresponds to this area, this corresponds to this area coming in, and this area corresponds to this area around the transition state. And so this red dot is the reaction coordinate. In this particular very simple case, we can really identify the reaction coordinate exactly. In a lot of more complicated cases, it's very difficult to identify the reaction coordinate, but you can usually get some kind of guess. People do this all the time. I keep telling you that there are these simulators who do these kinds of things, and that's exactly what they do a lot of the time. They sometimes by guess, sometimes with more evidence behind it, they pick a reaction coordinate or calculate a reaction coordinate for moving from one side of a reaction to the other. All right, so that's all I'm going to say about reaction coordinates. It's all qualitative at this point, but I think it's important that people have sort of pictures in their head for later use, right? If you go through a class like this, you probably don't remember the details after a while anyway, but you do remember the pictures, and you remember that somebody somewhere in some class said something about this topic, and then you can go back and look at the notes, or else at least get enough of the terminology to do a Google search and find out more about it. All right, so chemical reaction is a bond breaking and bond forming process, right? And a transition state is something halfway between the two. It's when the old bonds are breaking and the new bonds haven't yet completely formed. And so these I-ring quantities, delta G double dagger, delta H double dagger, delta S double dagger, are all the delta G, delta H, and delta S values that correspond to going from the reactants, let's say, up to the transition state, or else from the products on the other side up to the transition state. And therefore, we have some feeling. If we have some idea what this transition state is, then we have some feeling for what kinds of things make for a big delta H or a big delta S. So for the delta H idea, the main contribution is the changes in the bonding energy, right? If you've got a transition state that looks like this, where you don't have either bond formed anymore, then obviously you've gone up in energy. had to put energy in to partially break both of these bonds at once. On the other hand, if you're talking about the entropy change that took place in going from I2 plus Cl, where two molecules are completely free, to this transition state where, it's kind of a weak molecule, right? It's only one molecule, though, not two. So the delta S looks smaller for the transition state here than it did for the reactants. And likewise, over on the product side, you've got one lone atom and then one molecule, so you've got two separate molecules again. The product side also looks to have higher entropy than the transition state. So very often, the transition state has the lowest entropy, and the delta S double dagger is a negative quantity, yeah. So that's what this is showing here. On the reactant side, you've got two molecules. On the product side, you've got two molecules. But in between, the transition state is a rather restricted point. It's a single point, right? If you want to look at it this way, entropy is proportional to how much area you're taking up over here. And this is the reactant side, this is the product side. You've got a lot of area you can run around in, but right near the transition state, you don't have much area. It's a smaller zone or a smaller region, and therefore has smaller entropy. And so, in summary, the molecular features that control the thermodynamics of molecules also control the kinetics. If we understand the kinds of things that make for a big positive delta H or a big negative delta H bond energy changes mainly for molecules, and if we understand the kinds of things that give rise to either a positive or a negative delta S, changes in the ranges of the degrees of freedom, molecule numbers, or that means translational degrees of freedom, right? Rotations and vibrations. Then by thinking about the transition state, rather than about the reactants and products, we also know what controls the kinetics. So thermodynamics, I said before that thermodynamics informs the kinetics in a lot of ways rather than the other way around. Even though the thermodynamics is kind of embedded in the kinetics, very often it's the thermodynamics that we use to understand the kinetics, and this is mainly what I had in mind, that if you want to know when a reaction is going to be slow or large or fast, then one way to think about it is to get some idea what the transition state looks like, and then look at the transition state relative to both reactants and products, and you can get some feeling for how big these delta H's and delta S values are, and therefore how high that barrier is, basically. All right, we'll stop there for now, and then see if maybe we lecture a little bit longer for tomorrow.